For centuries, human understanding rested on a comfortingly simple assumption. Space is an empty, unchanging stage upon which the events of the cosmos unfold, and time is a universal, relentless clock ticking away at an absolute, unyielding pace. It was a clean, intuitive framework that governed our understanding of reality. Then came Albert Einstein, who shattered that intuition by revealing a radical, mind-bending truth. Space and time are not separate, static constructs. They are fused together into a dynamic, four-dimensional continuum known as space-time. This continuum is not merely a passive backdrop for existence, it is a physical entity. It can curve, stretch, ripple, and twist under the influence of mass and energy. Planets orbit stars not because they are pulled by an invisible, instantaneous force across a void, but because they are simply following the natural, straightest paths available through a geometric landscape that has been warped by heavy objects. This conceptual shift revolutionized modern physics, enabling us to predict the existence of black holes, accurately navigate the globe using satellite networks, and detect gravitational waves vibrating through the universe from cosmic collisions that occurred billions of years ago. Yet, despite more than a century of rigorous experimental validation, a profound and humbling paradox remains at the absolute core of physics. We can calculate the curvature of spacetime with breathtaking precision, but we still do not fully understand what spacetime actually is at its most fundamental level. When pushed to its extreme limits, our current mathematical models break down entirely, leaving us with deep, unresolved mysteries regarding the true structure of reality. Today we will explore spacetime, Einstein's idea that we still don't fully understand. If you want to join us as we dive deeper into these cosmic mysteries, feel free to like this video and subscribe to the channel, and don't forget to leave a comment below telling us where and when you are watching this. To comprehend how completely Albert Einstein shattered our understanding of reality, we must first travel back to the late 17th century, when Sir Isaac Newton constructed the foundation of classical physics. For over 200 years, Newton's masterpiece, the Philosophiae Naturalis Principia Mathematica, stood as the ultimate guide to the mechanics of the universe. Newton handed humanity a clear, elegant, and intensely satisfying picture of existence. In this Newtonian world, reality was built upon two unwavering, immutable pillars: absolute space and absolute time. To Newton, absolute space was an infinite, empty, three-dimensional stage. It existed independent of any physical matter placed within it. Whether filled with galaxies, stars, and planets, or completely devoid of all substance, space remained static, unyielding, and entirely unaffected by the physical phenomena occurring inside its vast boundaries. It provided a permanent, immutable coordinate system against which all motion could be measured with total certainty. An object was either truly at rest or truly in motion relative to this cosmic grid. Space was not an active participant in physical events, it was merely the silent, eternal container of reality. Equally fundamental to Newton's physics was the concept of absolute time. Newton famously described absolute, true, and mathematical time as something that flows uniformly of its own nature, completely independent of anything external. Imagine an invisible cosmic master clock ticking at the exact same rhythm throughout every corner of the universe. In the Newtonian framework, a second measured on Earth was precisely identical to a second measured near a distant star or inside a swirling nebula. Simultaneity was absolute and universal. If two events occurred at the exact same moment, every observer across the entire cosmos, regardless of their location, velocity, or gravitational environment, would agree that those two events happened simultaneously. This mechanical worldview was extraordinary in its predictive power. Newton's laws of motion, combined with his law of universal gravitation, reduced the intricate ballet of the cosmos to deterministic mathematics. Using these tools, astronomers could predict the motion of planets, calculate the orbits of moons, forecast the return of comets, and chart the trajectories of artillery shells with staggering accuracy. The universe was viewed as a colossal, predictable clockwork mechanism, set in motion by universal laws, operating within a fixed grid of absolute space, and governed by a single, unyielding flow of time. For centuries, this Newtonian framework appeared invincible. However, as the 19th century progressed, physics began to venture beyond the macroscopic motion of solid objects and into the ethereal world of electricity and magnetism. In the 1860s, Scottish physicist James Clerk Maxwell achieved one of the greatest triumphs in the history of science by unifying electricity, magnetism, and optics into a single cohesive mathematical framework, the Maxwell equations. Maxwell's equations demonstrated that electricity and magnetism were two manifestations of the same underlying force, the electromagnetic field. More astonishingly, his equations mathematically predicted that changing electric fields generate magnetic fields, and changing magnetic fields generate electric fields, giving rise to self-propagating electromagnetic waves. When Maxwell calculated the speed at which these electromagnetic waves travel through space, he arrived at a specific, fixed number, approximately 186,000 miles per second, or roughly 300,000 kilometers per second. This speed matched the experimentally measured speed of light. Light was not an isolated phenomenon, it was an electromagnetic wave. Yet, this monumental discovery introduced a deep, terrifying theoretical contradiction that threatened to tear classical physics apart at its seams. Maxwell's equations stated that light travels at a constant speed, but they did not specify a reference frame. In classical mechanics, speed is always relative. If a passenger throws a ball forward inside a train moving at 50 miles per hour, an observer standing on the platform measures the speed of the ball as the speed of the train plus the speed of the throw. Motion is strictly additive according to Galilean relativity. So, 19th century physicists naturally asked a fundamental question: speed relative to what? If light is a wave, what medium is it waving through? Ocean waves travel through liquid water. Sound waves travel through air, wood, or metal. Waves are mechanical disturbances propagating through a physical substance. It seemed unthinkable that light waves could travel across millions of miles of empty space from the Sun to the Earth without a supporting physical medium. To resolve this paradox while preserving Newton's absolute framework, classical physicists invented a hypothetical substance, the luminiferous ether. The ether was conceived as an invisible, weightless, frictionless, all-pervading fluid that filled every cubic inch of the universe, occupying the exact coordinates of Newton's absolute space. It was postulated to be incredibly rigid, to support the ultra-fast transverse vibrations of light, yet completely tenuous so that planets and asteroids could glide through it without experiencing any measurable drag or slowing down. Light, physicists argued, was simply vibrations propagating through this motionless, universal ether. Under this theory, the speed of light, calculated by Maxwell's equations, was its speed relative to the resting frame of the luminiferous ether. This theoretical solution restored harmony to classical physics, but it created an explicit, testable prediction. If the universe is filled with a stationary sea of luminiferous ether, and planet Earth is orbiting the Sun through this sea at roughly 18 miles per second, then Earth must be constantly moving through the ether. From the perspective of an observer on Earth, there should be an endless, measurable ether wind blowing past our planet. Much like a driver inside a convertible feels a headwind even on a completely calm day. Consequently, the measured speed of a beam of light should vary depending on the direction the light is traveling relative to Earth's movement through the ether wind. A beam of light fired parallel to Earth's motion through the ether should take longer to complete a round trip than a beam of light fired perpendicular to that motion. In 1887, two American physicists, Albert Michelson and Edward Morley, set out to detect this elusive ether wind once and for all. Conducting their work at the Case School of Applied Science in Cleveland, Ohio, they designed an instrument of unprecedented sensitivity, the Michelson interferometer. The design of the Michelson-Morley experiment was elegantly brilliant. The apparatus utilized a half-silvered mirror, known as a beam splitter, to split a single beam of light into two perpendicular pathways of equal length. One light beam traveled along an arm aligned parallel to Earth's orbital motion through space, while the second light beam traveled along an arm oriented at a right angle, perpendicular to the motion. Both beams struck mirrors at the ends of their respective pathways, reflected back, and recombined at the beam splitter before striking a detector screen. If the Earth were indeed moving through a stationary luminiferous ether, the ether wind would alter the relative speeds of the two light beams along their different paths. When the two beams recombined at the detector, their light waves would be slightly out of phase with one another. This phase difference would produce a distinct interference pattern, a characteristic series of alternating light and dark bands on the viewing screen. To rule out any subtle physical flaws or structural inequalities in the arms of the machine, the entire apparatus was mounted on a massive, heavy stone slab floating in a circular tub of liquid mercury. This allowed the entire experiment to be rotated smoothly through 360 degrees while taking continuous measurements. The Michelson-Morley interferometer was so extraordinarily sensitive that it could easily detect a shift in the interference pattern far smaller than what was expected from Earth's orbital motion through the ether. Physicists across the world eagerly anticipated the results, expecting the experiment to finally confirm the existence of the luminiferous ether and solidify Newton's absolute space as a physical reality. Instead, the experiment produced what is arguably the most famous and important null result in the history of science. No matter which direction the apparatus was rotated, no matter what time of day the test was performed, and no matter what season of the year the measurements were taken, as Earth moved to different positions in its orbit around the Sun, the result was always precisely the same. The interference pattern never shifted. The speed of light remained completely identical in all directions. There was no ether wind. There was no measurable drag. The luminiferous ether, the very substance invented to safeguard classical mechanics, simply was not there. The scientific community was plunged into a state of profound crisis. For nearly 2 decades, physicists attempted desperate theoretical gymnastics to save the concept of the ether. Some suggested that Earth somehow dragged the ether along with it through space, though this conflicted with astronomical observations of stellar aberration. Others, such as Hendrik Lorentz and George Fitzgerald, proposed that physical objects actually shrink in length when moving through the ether, and that moving clocks slow down by an exact factor that happened to perfectly conceal the ether wind from detection. While Lorentz developed brilliant mathematical transformation equations that correctly described these physical effects, these formulas were treated as artificial, mechanical tricks designed to save a failing theory. The central paradox remained unresolved, and classical physics found itself locked in a complete stalemate. Scientists were forced to confront a terrifying possibility. Either Maxwell's equations were wrong, or Newton's absolute space and time did not exist. Classical mechanics had reached its ultimate breaking point, setting the stage for a young Clerk working in a Swiss patent office to reimagine the fundamental nature of reality. In 1905, a 26-year-old technical examiner working at the Swiss patent office in Bern, named Albert Einstein, published a paper that shattered the impasse gripping theoretical physics. Titled "On the Electrodynamics of Moving Bodies," the paper offered a solution that was breathtaking in its simplicity and radical in its consequences. Einstein proposed that physics did not need complex, unobservable mechanisms like the luminiferous ether or arbitrary physical contractions to explain the results of optical experiments. Instead, he suggested that scientists needed to abandon the deeply ingrained assumptions of absolute space and absolute time. Einstein built his special theory of relativity upon 2 deceptively simple postulates. The first postulate, known as the principle of relativity, asserted that the laws of physics are identical in all inertial reference frames, that is, in all frames of reference moving at a constant velocity without acceleration. An observer inside a smoothly gliding sealed train car experiences the exact same laws of physics as an observer standing still on a station platform. There is no preferred stationary frame of reference in the universe by which absolute motion can be measured. The second postulate was even more revolutionary. The speed of light in a vacuum is a constant, universally denoted as the letter c, approximately equal to 186,000 miles per second. Crucially, this speed remains identical for all observers, regardless of the velocity of the light source or the velocity of the observer. To grasp how profound this postulate is, consider a classical scenario. If a baseball pitcher stands on a train moving at 50 miles per hour and throws a ball forward at 80 miles per hour, an observer standing on the ground measures the ball's speed as 130 miles per hour. Speeds add up linearly in everyday experience. However, under Einstein's second postulate, light completely defies this common sense. If a spaceship traveling at 90% of the speed of light fires a laser beam forward, an observer at rest does not measure the laser beam as traveling at 190% of the speed of light. The observer measures the light traveling at precisely c. Even more strangely, the astronauts on board the spaceship also measure the exact same laser beam moving away from them at precisely c. Because speed is defined as distance traveled divided by time elapsed, maintaining a constant speed of light for all observers requires something fundamental to yield. If the speed of light cannot change, then space and time themselves must adjust dynamically depending on the relative motion of the observers. From this simple realization emerged one of the most astonishing consequences of special relativity: time dilation. Time dilation dictates that a clock in motion ticks more slowly when measured by a stationary observer relative to that clock. Time is not a universal, steady river flowing at the same rate everywhere. Instead, the rate at which time passes for any object depends directly on how fast that object is moving through space. The faster an object moves through space, the slower it moves through time relative to an observer at rest. While this concept sounds like science fiction, it is a thoroughly tested, routinely measured physical reality. One of the most compelling laboratory demonstrations of time dilation involves subatomic particles called muons. Muons are unstable elementary particles created high in Earth's upper atmosphere, roughly 6 to 10 miles above the surface, when high-energy cosmic rays collide with atomic nuclei in the air. At rest in a laboratory, a muon has a notoriously brief mean lifespan of approximately 2.2 microseconds before it spontaneously decays into an electron and two types of neutrinos. Even if a muon travelled at nearly the speed of light, roughly 99.9% of gas, 2.2 microseconds is only long enough for it to travel a distance of approximately 2,000 feet, or less than half a mile before decaying. Mathematically, almost no muons generated in the upper atmosphere should ever survive long enough to reach detector stations located at sea level. Yet experiments consistently detect vast quantities of muons striking Earth's surface every second. This apparent paradox is entirely resolved by time dilation. Because atmospheric muons travel toward the ground at relativistic speeds, extremely close to the speed of light, their internal clocks tick dramatically slower relative to ground-based observers. From the frame of reference of scientists on Earth, the lifetime of the fast-moving muon is stretched out by a mathematical factor known as the Lorentz factor. Instead of decaying in 2.2 microseconds, the muon's extended clock allows it to survive long enough to traverse the entire 10-mile journey through the atmosphere and reach the ground. Conversely, from the muon's own frame of reference, its lifetime remains a normal 2.2 microseconds, but it perceives the distance to Earth as severely compressed, an effect known as length contraction, allowing it to cover the distance before decaying. Both perspectives yield the exact same physical outcome, proving that time rate is strictly relative. To demonstrate time dilation on a macroscopic scale using human technology, scientists turned to atomic clocks, devices capable of measuring time with extraordinary precision by counting the hyperfine transition frequencies of atoms such as cesium. In 1971, physicists Joseph Haffel and Richard Keating performed a historical experiment designed to test Einstein's predictions directly on a global scale. Haffel and Keating took 4 highly accurate cesium beam atomic clocks aboard commercial airliners and flew them completely around the world twice, once eastward and once westward. They then compared the time recorded on the airborne clocks against reference atomic clocks that remained stationary at the United States Naval Observatory in Washington, D.C. Because Earth is rotating on its axis, an aircraft flying eastward travels in the same direction as Earth's rotation, giving it a higher speed relative to a non-rotating, inertial reference frame centered at the planet's core. An aircraft flying westward travels against Earth's rotation, resulting in a lower speed relative to that same frame. When the airborne clocks return from their global journeys, Their readings were carefully compared to the ground clocks. The results matched Einstein's relativistic equations to incredible precision. The clocks that flew eastward, travelling at higher relative speeds, had lost time relative to the ground clocks, while the clocks that flew westward had gained time relative to the ground reference. The experiment proved beyond any doubt that mechanical and atomic processes slow down in direct accordance with the predictions of special relativity, confirming that moving through space alters an object's progression through time. Time dilation is only one half of the fundamental transformation required by special relativity. Because the speed of light must remain constant for all observers regardless of their motion, space itself must also adjust alongside time. This spatial counterpart to time dilation is known as length contraction, or Fitzgerald-Lorentz contraction. Length contraction dictates that the physical length of an object measured by a stationary observer becomes shorter along the direction of its motion as the object's speed approaches the speed of light. This contraction is not an optical illusion, a distortion caused by the light taking time to reach an observer's eyes, or a physical mechanical compression caused by atmospheric resistance. It is a fundamental geometrical property of space itself. An object moving relative to an observer literally occupies less distance in space along its axis of motion within that observer's reference frame. At everyday human speeds, length contraction is completely imperceptible. A car travelling down a highway at 60 miles per hour shortens by an amount far smaller than the diameter of a single subatomic proton. However, as an object approaches relativistic speeds, fractions of the speed of light, the effect becomes dramatic. If a physical ruler or a starship measuring 100 meters long at rest could be accelerated to 90% of the speed of light relative to an observer, that observer would measure the passing starship to be only 43.6 meters long. If its speed increased to 99% of the speed of light, its measured length would shrink to just 14.1 meters. This spatial adjustment ensures that physical laws remain consistent across different frames of reference. Returning to the example of atmospheric muons, an observer standing on Earth explains the muon's survival by observing time dilation. The muon's internal clock runs slowly, allowing it to survive the long journey through 10 miles of atmosphere. However, from the rest frame of the muon itself, the particle is completely stationary, and its internal clock ticks at its normal, undilated rate. How, then, does the muon explain its ability to reach Earth's surface before decaying? From the muon's perspective, Earth and its entire atmosphere are rushing toward the muon at over 99% of the speed of light. Due to length contraction, the 10-mile thick layer of atmosphere shrinks from the muon's viewpoint to a fraction of a mile. The muon survives not because its lifetime has been stretched, but because the distance it must travel has been severely compressed. Both observers calculate the exact same physical event, the muon striking the ground, yet one perceives time stretching while the other perceives space shrinking. These twin phenomena of time dilation and length contraction revealed that space and time can no longer be treated as independent, rigid dimensions. In 1908, the German mathematician Hermann Minkowski provided the mathematical synthesis that unified these concepts into a single, cohesive framework. Minkowski famously declared that henceforth space by itself and time by itself were doomed to fade away into mere shadows, and only a kind of union of the two would preserve an independent reality. Minkowski introduced the concept of the spacetime continuum, a four-dimensional mathematical manifold that combines three spatial dimensions, length, width, and height, with a single temporal dimension, time. In this four-dimensional geometric framework, an event is not defined merely by where it happens or when it happens, but by its precise location in spacetime, expressed as a set of four coordinates. Within Minkowski spacetime, objects do not simply move through space as time ticks away separately. Instead, all physical entities possess a four-dimensional vector of motion called a four-velocity, and every object is constantly moving through spacetime at a single, unchanging, invariant speed, the speed of light. This concept completely redefines our understanding of motion. Imagine driving a car on a vast, flat plain at a locked cruise control speed of 60 miles per hour. If you drive due north, your entire speed of 60 miles per hour is directed northwards. If you turn slightly northeast, some of your speed is directed east, which reduces your speed toward the north. In Minkowski spacetime, every physical object moves through the 4 dimensions of spacetime at the exact fixed speed of c. If an object is completely at rest relative to an observer, all of its motion through spacetime is directed purely along the temporal dimension. It moves through time at the maximum possible rate. However, if the object begins moving through space relative to that observer, a portion of its motion through spacetime must be diverted away from time and redirected into space. Because part of its fixed speed is now being used to travel through space, its progression through time must slow down relative to the observer. This spatial motion steals from temporal motion. The faster an object moves through space, the slower it moves through time. And if an object could reach the speed of light in space, like a photon, its motion through time would cease entirely. The 4-dimensional geometry of spacetime also dismantled another fundamental pillar of classical physics, the concept of absolute simultaneity. In Newtonian physics, if 2 firecrackers explode at the exact same moment on opposite sides of a room, everyone in the universe agrees that the explosions occurred simultaneously. In Minkowski spacetime, absolute simultaneity does not exist. Because space and time mix dynamically depending on an observer's motion, 2 events that appear to happen at the exact same time to a stationary observer will happen at different times to an observer in motion. Whether event A happens before event B, after event B, or simultaneously with event B depends entirely on the observer's frame of reference. This realization leads directly to the block universe concept, or eternalism. In a 4-dimensional spacetime continuum, the distinction between the past, the present, and the future is merely a stubborn, persistent illusion. The past is not gone, and the future is not unwritten. All moments in time, from the Big Bang to the distant heat death of the cosmos, exist simultaneously as a static, 4-dimensional geometric landscape. Special relativities successfully unified space and time into a single physical entity and explained how electromagnetism operates without needing an ether. Yet, special relativity possessed a glaring, critical limitation. It applied strictly to special cases, constant uniform velocities without acceleration, and completely flat spacetime. It lacked any mechanism to explain gravitational forces or accelerating objects. Einstein realized his work was incomplete, setting him on a decade-long intellectual journey to expand his framework to incorporate gravity, ultimately producing the general theory of relativity. While special relativity brilliantly unified space and time into a 4-dimensional continuum and harmonized electromagnetism with motion, Albert Einstein recognized a glaring, fundamental flaw in his own creation. As the name implied, special relativity was restricted to a very special, idealized set of conditions. It applied exclusively to inertial frames of reference, systems moving at smooth, constant velocities relative to one another, entirely free from acceleration. Furthermore, special relativity completely failed to account for gravity. In Newton's classical framework, gravity was modeled as a mutual, instantaneous force of attraction between masses, acting across empty space. If the Sun were to suddenly vanish, Newton's equations dictated that Earth would immediately fly off its orbit in a straight tangent line at that exact fraction of a second. But special relativity established that no physical signal, force, or information can travel faster than the speed of light in a vacuum. If gravity acted instantaneously across vast distances, it directly violated the universal speed limit set by c. Einstein realized that to build a comprehensive physics of reality, he had to resolve 2 deep questions. How does gravity actually transmit its influence through space? And how do the laws of physics behave in accelerating frames of reference? The breakthrough came in 1907 through what Einstein would later describe as the happiest thought of his life. Einstein conducted a simple thought experiment. Imagine a person standing inside a closed elevator cab floating deep in interstellar space, far away from any stars or planets. There is no gravitational field. If the person lets go of a ball, the ball floats weightlessly beside them. If the person jumps, they float gently to the top of the cabin. Floating in deep space produces total weightlessness. Now imagine that a powerful rocket engine attached to the bottom of the elevator cab suddenly fires, accelerating the elevator upward through space at a constant rate of 32 feet per second squared, precisely 9.8 meters per second squared. What does the person inside feel? The floor of the accelerating elevator pushes upward against the soles of their feet. If they drop a ball, the ball does not float. The floor accelerates upward to meet the ball, making it appear to fall to the ground at 9.8 meters per second squared. If the person steps on a bathroom scale, it registers their normal weight on Earth. If the cab has no windows, is there any local physical experiment the occupant can perform to determine whether they are floating in an accelerating rocket in deep space, or sitting completely stationary in a uniform gravitational field on the surface of Earth? Einstein concluded that the answer was an absolute no. The physical effects of uniform acceleration are completely indistinguishable from the physical effects of a uniform gravitational field. This fundamental insight became known as the equivalence principle. Inertial mass, the property of an object that resists acceleration when pushed, is identical to gravitational mass, the property of an object that responds to a gravitational field. The equivalence principle allowed Einstein to make an astounding theoretical leap. If acceleration bends the path of light, then gravity must also bend the path of light. Imagine a beam of light fired horizontally from one wall of the accelerating elevator cab to the opposite wall. Because the elevator is accelerating upward while the light is in transit, the opposite wall moves upward before the light hits it. An observer inside the accelerating elevator sees the light beam trace a downward curved arc toward the floor. Because the equivalence principle states that an accelerating reference frame is physically equivalent to a gravitational field, Einstein realized that a gravitational field must also bend light. Light always travels along the shortest, most efficient path between 2 points, a geometric trajectory known in mathematics as a geodesic. In flat space, a geodesic is simply a straight line. If light bends in the presence of gravity, but light must follow a geodesic, then gravity is not a physical force pulling on the light at all. Instead, gravity must be warping the very geometry through which light travels. This realization led Einstein to completely redefine gravity in his general theory of relativity, published in 1915. Gravity is not an invisible, instantaneous force pulling distant masses across empty space, as Sir Isaac Newton had claimed. Gravity is a structural manifestation of four-dimensional space-time geometry. Mass and energy warp, curve, and distort the fabric of space-time around them, and that curvature dictates how objects move. Physicist John Archibald Wheeler famously summarized this revolutionary concept in a single concise sentence. Matter tells space-time how to curve, and space-time tells matter how to move. To visualize this four-dimensional phenomenon using a simplified two-dimensional analogy, imagine a tightly stretched sheet of flexible rubber. If the rubber sheet is empty, it remains completely flat. A small marble rolled across the flat sheet will travel in a clean, straight line. Now place a heavy bowling ball in the center of the rubber sheet. The weight of the bowling ball creates a deep, curved depression in the flexible material. If you now roll a small marble across the sheet, the marble no longer travels in a straight line. As it enters the depression created by the bowling ball, its trajectory curves toward the central weight. If the marble has the right speed and angle, it will roll continuously around the central slope, entering a stable orbit around the bowling ball. To an observer looking from far above who cannot see the clear rubber sheet, it appears as though the heavy bowling ball is exerting an invisible, attractive pull on the small marble. But in reality, there is no pull. The bowling ball simply curved the surface, and the marble is merely following the straightest available geometric path, a geodesic, across that warped surface. In the four-dimensional reality of our universe, massive objects like stars, planets, and galaxies distort the four-dimensional space-time surrounding them. When Earth orbits the Sun, it is not being dragged by a physical string of Newtonian gravity. Earth is simply moving along its natural, unforced geodesic path through a four-dimensional valley in space-time created by the immense mass of the Sun. This structural model of gravity fundamentally changed our understanding of time as well. Because gravity is the curvature of space-time, and space-time unifies space and time together, a strong gravitational field does not merely bend space, it also slows down the passage of time. This effect is known as gravitational time dilation. The closer an object is to a massive body, the deeper it rests within a gravitational potential well, and the stronger the curvature of space-time it experiences. 20. Time runs measurably slower near a heavy object than it does further away in weaker gravity. A clock sitting on a beach at sea level, close to Earth's centre of mass, ticks slightly slower than a clock placed on top of Mount Everest. Gravitational time dilation is a direct, unavoidable consequence of the equivalence principle. Returning to the accelerating elevator cab in deep space, imagine a clock mounted on the ceiling, sending light pulses at regular intervals to a clock mounted on the floor. Because the floor is constantly accelerating toward the incoming light pulses, the floor clock receives the pulses at a faster rate than they were emitted, recording time as moving faster at the top than at the bottom. By equivalence, time must pass slower at the bottom of a gravitational field than at the top. General relativity completely transformed theoretical physics from a study of forces acting within a rigid arena into a study of geometry itself. Space and time were no longer passive containers, they were dynamic, active participants in physical events, able to be stretched, squeezed, bent and twisted by the energy contained within the cosmos. Yet, this radical new geometric theory needed rigorous empirical proof to convince a scientific world still firmly rooted in Newtonian physics. When Albert Einstein presented his general theory of relativity to the Prussian Academy of Sciences in November 1915, it stood as a triumph of theoretical imagination. However, theoretical elegance alone does not constitute scientific truth. For general relativity to replace Sir Isaac Newton's long-cherished mechanical framework, it had to make precise, quantitative predictions that could be put to the test through observational evidence. Einstein proposed 3 distinct empirical tests that his theory had to pass: explaining the anomaly in the orbit of Mercury, measuring the deflection of starlight passing near the Sun, and observing the gravitational redshift of light. The first major victory for general relativity involved a long-standing astronomical mystery that had baffled scientists for decades: the orbital anomaly of the planet Mercury. According to Newton's law of universal gravitation, a single planet orbiting a star traces out a perfect, unchanging ellipse. However, because our solar system contains multiple planets, the gravitational pulls of Venus, Earth, Jupiter, and other celestial bodies exert tiny perturbing forces on Mercury. These perturbations cause Mercury's elliptical orbit to slowly rotate or precess over time. This means that the point of closest approach to the Sun, known as the perihelion, advances slightly with every orbit. By the mid-19th century, astronomers using precise telescope measurements calculated that Mercury's perihelion precessed by 574 arcseconds per century. When French mathematician Urbain Le Verrier used Newton's equations to calculate the expected gravitational influence of all the known planets, he accounted for 531 arcseconds per century. This left a tiny, stubborn discrepancy of approximately 43 arcseconds per century that Newtonian mechanics could not explain. Desperate to save Newton's model, 19th-century astronomers hypothesized the existence of an undiscovered hidden planet orbiting even closer to the Sun, which they named Vulcan. They reasoned that Vulcan's gravitational pull was responsible for the extra 43 arcseconds of precession. For decades, astronomers searched the glare of the Sun during solar eclipses, but Vulcan was nowhere to be found. It was a ghost planet invented solely to compensate for a failing physical law. In November 1915, Einstein applied the complex field equations of general relativity to the orbit of Mercury. Under general relativity, the Sun's massive density curves spacetime deeply in its immediate vicinity. Because Mercury orbits closer to the Sun than any other planet, it passes directly through this heavily warped spacetime region, where Newtonian mechanics no longer holds true. When Einstein completed his arduous calculations, the spacetime curvature generated by the Sun yielded an additional precession of precisely 43 arcseconds per century, matching the observed discrepancy exactly, with no need for an imaginary planet. Einstein later recalled that when he saw the math align perfectly with reality, he felt a surge of joy so intense it gave him heart palpitations. While solving Mercury's orbit was a monumental success, it was a hindcast, explaining data that was already known. To truly prove general relativity, Einstein needed to predict a completely new, unobserved phenomenon that could be tested. That prediction was the gravitational deflection of light. According to general relativity, a massive body curves the spacetime around it, causing straight paths, geodesics, to bend. When starlight travels past the edge of a massive object like the Sun on its way toward Earth, the light must follow the curved geometry of spacetime, causing the light beam to bend inward. Newton's corpuscular light theory also predicted a slight deflection of light, but Einstein's equations showed that the geometric warping of space and time together produced a deflection angle precisely twice as large as the Newtonian prediction, approximately 1.75 arcseconds for starlight grazing the solar limb. Testing this prediction posed a severe observational challenge. Under normal conditions, the brilliant glare of the Sun completely drowns out the light from distant stars in the daytime sky. The only way to observe stars appearing right next to the edge of the Sun is during a total solar eclipse, when the Moon temporarily blocks the solar disk. In May 1919, British astronomer Sir Arthur Eddington led a famous scientific expedition to test Einstein's prediction. Eddington travelled to the island of Principe off the western coast of Africa, while a second team, led by Andrew Crommelin, travelled to Sobral in northern Brazil. Their goal was to photograph a cluster of stars known as the Hyades during a total solar eclipse and compare their measured positions to nighttime photographs taken of the exact same star field months earlier, when the Sun was in a different part of the sky. If general relativity was correct, the Sun's space-time curvature during the eclipse would push the apparent positions of the stars slightly outward, away from the solar limb. Despite encountering overcast weather and cloudy skies, both teams succeeded in obtaining high-quality photographic plates. When Eddington carefully measured the positions of the stars on the plates, the results were decisive. The apparent displacement of the stars matched Einstein's prediction of 1.75 arcseconds with an experimental error, completely ruling out the Newtonian prediction. In November 1919, the Royal Society of London formally announced the results. The headline in the New York Times declared, "Lights all askew in the heavens, Einstein theory triumphs." Almost overnight, Albert Einstein was transformed into a global scientific icon, and the fundamental structure of space and time was permanently altered. In the decades that followed, technology advanced, providing increasingly precise validations of general relativity. In 1959, physicists Robert Pound and Glenn Rebka performed an extraordinary terrestrial test at Harvard University, known as the Pound-Rebka experiment. They aimed to measure gravitational redshift, the slowing down of time caused by gravity. According to general relativity, a photon of light climbing out of a gravitational well loses energy. Because the energy of a light wave is directly proportional to its frequency, losing energy causes the light's frequency to decrease and its wavelength to stretch, shifting the light toward the red end of the electromagnetic spectrum. Conversely, light falling downward into a gravitational field gains energy, shifting toward higher frequencies. Pound and Rebka mounted a precise gamma-ray emitter at the top of a 73-foot tower in the Jefferson Physical Laboratory and placed a sensitive detector at the basement floor below, measuring the minute frequency shift of photons falling down the tower through Earth's gravitational field. The altitude change was extremely modest, resulting in a fractional frequency change of less than 1 part in 100 trillion. Yet, using the Mossbauer effect, Pound and Rebka measured the frequency shift with stunning precision, finding that it matched the exact mathematical prediction of gravitational time dilation. Today, general relativity is no longer just an abstract subject for academic research or astronomical observations. It is an absolute operational requirement for modern daily technology. The most prominent example is the Global Positioning System, or GPS. The GPS network relies on a constellation of over 30 satellites orbiting Earth at an altitude of approximately 12,500 miles, traveling at velocities of around 8,700 miles per hour. Each satellite carries ultra-precise atomic clocks that continuously broadcast time-stamped signals to receiver units in smartphones, automobiles, and aircraft. To pinpoint a user's position on Earth's surface down to a few feet, a receiver calculates the exact time delay it takes for radio signals traveling at the speed of light to arrive from at least 4 separate satellites. Because GPS operations depend entirely on nanosecond precision, engineers must account for both special and general relativity. Under special relativity, because the satellites are moving at high orbital speeds relative to an observer on the ground, their onboard atomic clocks tick slower due to velocity time dilation, losing roughly 7 microseconds per day compared to ground clocks. However, general relativity introduces a competing and much larger effect. Because the satellites orbit 12,500 miles above Earth, they experience a significantly weaker gravitational field than clocks sitting on the planet's surface. As a result of gravitational time dilation, time runs faster for the satellite clocks than for Earth-bound clocks, causing them to gain approximately 45 microseconds per day. When you combine these two opposing relativistic effects, -7 microseconds from special relativity and +45 microseconds from general relativity, the net result is that atomic clocks on board GPS satellites run fast by 38 microseconds every single day. 38 microseconds may sound like a negligible blink of an eye, but because light travels at 186,000 miles per second, an uncorrected time error of 38 microseconds would accumulate a location positioning error of roughly 7 miles every single day. Within a week, navigation apps would be completely useless, directing drivers into lakes or pointing ships miles off course. Every GPS satellite is explicitly programmed to offset its internal clock frequencies before launch to compensate for these exact relativistic time shifts. Through Mercury's orbit, Eddington's eclipse, laboratory experiments, and satellite navigation networks, general relativity proved that space-time curvature is a real physical reality. Yet, as physicists pushed these geometric equations to their ultimate mathematical limits, they discovered places where the equations yielded absurd, infinite values, exposing deep structural boundaries where our understanding of space-time collapses entirely. When Albert Einstein published his general theory of relativity, he viewed it primarily as a smooth, continuous description of space-time geometry. Yet, embedded within his own field equations lay a terrifying prediction that Einstein himself struggled to accept. Under extreme conditions, the fabric of space-time can buckle, fold in on itself, and completely collapse. Just months after Einstein presented his theory in 1915, the German physicist and astronomer Karl Schwarzschild, while serving on the front lines of World War I, derived the first exact, non-trivial solution to Einstein's field equations. Schwarzschild was calculating the gravitational field surrounding a simple, non-rotating spherical mass. His mathematical calculations produced a pristine description of space-time curvature around stars and planets. However, his formulas contained a bizarre mathematical feature. If a mass were compressed below a specific critical radius, now known as the Schwarzschild radius, the equations went wild. If a mass becomes sufficiently dense, its gravitational pull becomes so overwhelming that space-time curves infinitely inward. This theoretical region became known as a black hole, a term coined decades later by physicist John Archibald Wheeler. A black hole represents a region of space where gravity is so intense that nothing, not even light, the fastest entity in the universe, can escape its grasp. The boundary defining the outer edge of a black hole is known as the event horizon. The event horizon is not a physical, solid surface made of matter. It is a mathematical and causal boundary in space-time. It represents the absolute point of no return. Outside the event horizon, an object can still fire its thrusters or use energy to escape the black hole's gravitational pull. Once an object crosses inside the event horizon, all paths through four-dimensional space-time lead relentlessly toward the center. To understand why escape becomes impossible beyond the event horizon, one must examine how extreme gravity fundamentally alters the geometry of light cones in Minkowski spacetime. Outside a black hole, an object has freedom of movement in space. Its light cone points forward into a future that contains many possible spatial directions. However, as an object approaches the event horizon, the intense curvature of spacetime tilts its light cone inward toward the central mass. At the exact boundary of the event horizon, the light cone tilts so severely that the spatial direction toward the center of the black hole becomes synonymous with the temporal direction into the future. Inside the event horizon, moving toward the central core is no longer a choice of direction in space. It becomes as inevitable as moving forward in time. Just as you cannot turn around and travel into yesterday, an object inside an event horizon cannot turn around and travel outward toward space. The radial coordinate toward the center becomes a temporal coordinate, moving inexorably forward. For an observer watching an astronaut fall toward a supermassive black hole from a safe distance, gravitational time dilation creates a surreal, mind-bending visual illusion. Because time passes dramatically slower in stronger gravitational fields, the distant observer sees the falling astronaut's clock tick slower and slower as they approach the event horizon. Furthermore, the light emitted by the astronaut stretches to longer, redder wavelengths due to extreme gravitational redshift. As the astronaut reaches the event horizon, time for them appears to come to a complete halt from the perspective of the outside observer. The astronaut seems to freeze right at the boundary, fading away into a faint infrared blur as the light waves stretch toward infinity. The distant observer never actually sees the astronaut cross the event horizon. However, the experience of the falling astronaut is radically different. According to the principle of relativity, the astronaut feels no local change in the flow of their own time. Their wristwatch continues to tick normally, 1 second per second. As they cross the event horizon, they notice no physical barrier, signboard or wall. Unless the tidal forces are severe, the astronaut glides across the event horizon in a finite amount of proper time. If the black hole is small, such as a stellar mass black hole created by the collapse of a dying star, the astronaut faces an excruciating physical phenomenon known as spaghettification, or the tidal effect. Because the strength of gravity varies inversely with the square of the distance, the gravitational pull exerted on the astronaut's feet is vastly stronger than the pull on their head. As they plunge downward, this extreme gravitational gradient stretches their body vertically while squeezing it horizontally, pulling them into a long, thin string of fundamental particles long before they reach the center. Conversely, around a supermassive black hole containing millions or billions of solar masses, the event horizon is so immense that the tidal forces at the boundary are gentle, allowing an observer to cross safely without being torn apart, though their ultimate fate inside remains sealed. At the very heart of a black hole lies the most problematic concept in modern theoretical physics, the gravitational singularity. According to classical general relativity, once mass collapses inside an event horizon, no known force in nature can halt its inward trajectory. The matter continues to collapse down to a point of zero volume, resulting in an infinitely dense mathematical point. At this singularity, the curvature of spacetime becomes infinite, the density becomes infinite, and the strength of gravity becomes infinite. In mathematics, an infinity in a physical equation is not a feature, it is a red flag. It signals a breakdown of the mathematical system itself. At a singularity, the smooth geometric canvas of general relativity tears apart, and the laws of physics lose all predictive power. Equations yield nonsense, time effectively ceases to exist, and space loses its classical meaning. It is crucial to emphasize that a singularity is likely not a real, physical object made of infinite matter sitting inside a black hole. Rather, the appearance of a singularity indicates a profound limitation in Einstein's general theory of relativity. General relativity is a classical, continuous field theory that completely ignores the quantum nature of reality at microscopic scales. When immense mass is squeezed into a volume smaller than a subatomic particle, quantum mechanics must come into play. However, because general relativity and quantum mechanics are mathematically incompatible, physics currently lacks a unified theory of quantum gravity capable of describing what actually resides at the center of a black hole. Black holes represent the absolute limit of classical spacetime geometry. They demonstrate that when gravity is pushed to its extreme, Spacetime can wrap itself into a closed pocket, hiding a region of reality behind an event horizon where our current understanding of the universe grinds to a complete halt. Yet, static black holes are not the only extreme manifestation of spacetime. When massive objects rotate or collide, they set the dynamic fabric of reality into violent motion. While a static black hole bends spacetime inward toward a central point, a rotating massive object introduces a far more dynamic and bizarre distortion into the fabric of reality. In classical physics, an object spinning in space merely rotates within a passive, stationary background. But under general relativity, space and time are not passive. When a massive celestial body rotates, it drags the surrounding structure of spacetime along with it, twisting the very geometry of the cosmos. This phenomenon is known as frame dragging, or mathematically as the Lense-Thirring effect. To visualize frame dragging, imagine a heavy sphere submerged in a thick tub of viscous honey. If the sphere remains completely still, the honey surrounds it in a uniform, undisturbed state. But if you begin to rapidly rotate the sphere, the sticky honey directly touching its surface gets pulled into motion. As the sphere continues to spin, it drags successive layers of honey around with it, creating a swirling vortex in the fluid. In our universe, space-time behaves much like that thick fluid. A spinning object, whether a planet, a neutron star, or a rotating black hole, literally twists the four-dimensional space-time grid surrounding it. An observer falling straight down toward a rotating planet would find themselves forced to rotate along with the planet's spin relative to distant stars, even if they fired rockets to prevent any angular rotation of their own. Space itself is moving, and everything within that space is carried along by the geometric whirlpool. For decades, frame dragging remained a purely theoretical deduction, derived from Roy Kerr's 1965 mathematical solution to Einstein's field equations, which described rotating black holes. To test whether frame dragging occurs in the real universe, National Aeronautics and Space Administration launched a dedicated space mission in 2004, known as Gravity Probe B. Gravity Probe B was one of the most technologically demanding experiments ever flown in space. The satellite carried 4 pristine, ultra-precise quartz gyroscopes, which were coated in niobium and cooled with liquid helium to near absolute zero. These gyroscopes held the record for the most perfectly spherical manufactured objects in human history. The spacecraft was placed into a polar orbit around Earth, with its guide telescope aligned precisely toward a distant reference star named IM Pegasi. If Earth did not warp or twist spacetime, the spinning gyroscopes would maintain their directional orientation toward the reference star indefinitely as Earth rotated beneath them. However, general relativity predicted 2 distinct geometric effects that would alter the gyroscope's axes over time. The first was the geodetic effect, the bending of spacetime caused simply by Earth's mass, which was predicted to tilt the gyroscopes by roughly 6.6 arcseconds per year. The second was frame dragging, the physical twisting of spacetime caused by Earth's rotation, which was predicted to produce a tiny additional shift of just 0.039 arcseconds per year. Measuring an angle as minuscule as 0.039 arcseconds is equivalent to measuring the thickness of a single human hair viewed from a distance of over 10 miles. Yet, after years of painstaking data analysis to eliminate background noise, the Gravity Probe B team confirmed both predictions. Earth's rotation does indeed drag the fabric of spacetime around with it, proving that spacetime is an active, malleable medium susceptible to mechanical torsion. Around a rapidly rotating Kerr black hole, frame dragging reaches its most violent, extreme limit. Surrounding the event horizon of a rotating black hole lies a region known as the ergosphere. Within the ergosphere, the twisting of spacetime is so intense that space itself is dragged along at speeds exceeding the speed of light relative to distant universe observers. Inside this region, it is physically impossible for any object to remain stationary relative to the distant stars. Matter and light are irrevocably forced to orbit in the direction of the black hole's rotation. Frame dragging demonstrates that spacetime can be twisted by rotating mass. But when massive objects undergo extreme acceleration, such as 2 black holes or neutron stars spiraling inward toward a catastrophic merger, they create an even more profound disturbance, Gravitational waves. In 1916, Albert Einstein realized that his field equations predicted the existence of gravitational radiation. Just as accelerating electric charges emit electromagnetic waves, accelerating massive objects emit gravitational waves. These waves are not vibrations traveling through matter or fields existing within space. They are dynamic ripples in the physical fabric of space-time itself, propagating outward through the cosmos at the exact speed of light. As a gravitational wave travels through space, it alternately stretches and compresses the geometry of space-time in directions perpendicular to its path of propagation. If a gravitational wave passes directly through a room, a circular ring of suspended particles would temporarily morph into an all-thin vertical ellipse, then contract into a short, wide horizontal ellipse, before returning to a circle. Crucially, the particles are not moving through space due to an applied physical force. Space itself is expanding in one direction, while contracting in the perpendicular direction. Because space-time is an extraordinarily stiff, rigid medium, generating gravitational waves of measurable size requires truly immense cosmic events, involving immense masses accelerating at relativistic speeds. For a century after Einstein's theoretical prediction, detecting these waves appeared technologically impossible. By the time gravitational waves generated by distant cosmic collisions travel millions or billions of light-years to reach Earth, their amplitude diminishes to a fraction of a subatomic scale. A passing gravitational wave compresses and stretches a distance of several miles by an amount thousands of times smaller than the diameter of a single atomic proton. In the late 20th century, physicists designed the Laser Interferometer Gravitational Wave Observatory, or LIGO, to meet this incredible engineering challenge. LIGO operates two twin detector facilities located thousands of miles apart in Hanford, Washington, and Livingston, Louisiana. Each facility consists of a massive L-shaped vacuum chamber with two perpendicular arms measuring 4 kilometers or 2.5 miles in length. LIGO uses ultra-pure laser beams split down both 4-kilometer arms, reflecting back and forth between isolated, heavy mirrors suspended on complex anti-vibration systems. When no gravitational wave is present, the laser beams recombine at a central detector in complete destructive interference, producing no signal. But when a gravitational wave passes through the observatory, it momentarily stretches one 4-kilometer arm while compressing the other perpendicular arm by a tiny fraction of a proton's width. This minute difference in length alters the travel time of the laser beams, causing them to fall out of phase and creating a clear, measurable interference light pattern at the detector. On September 14, 2015, LIGO achieved one of the most significant triumphs in the history of experimental physics. Both detectors recorded a distinct, rising wave signal known as a chirp. The signal, designated GW150914, matched the exact mathematical signature predicted by general relativity for the binary merger of two massive black holes. Approximately 1.3 billion years ago, two distant black holes, one containing roughly 29 solar masses and the other 36 solar masses, spiraled inward toward each other at nearly the speed of light before colliding and coalescing into a single, massive black hole of 62 solar masses. In the final fraction of a second before the collision, the violent interaction converted 3 full solar masses of pure matter directly into gravitational wave energy, according to Einstein's famous equation. For a brief moment, the power output of this single gravitational wave event exceeded the combined luminous power output of all the stars in the entire observable universe. The detection of gravitational waves opened an entirely new window onto the cosmos. For thousands of years, humanity explored the universe purely by observing light and electromagnetic radiation. With LIGO and subsequent detectors like Virgo and Cagra, scientists can now listen to the ripples of spacetime itself, observing black hole collisions, neutron star mergers, and the dynamic behavior of gravity under the most extreme conditions imaginable. Yet, as extraordinary as these localized phenomena are, the true scale of spacetime reveals itself when we turn our attention away from individual stars and black holes to examine the geometry of the entire universe as a whole. When we elevate our perspective from individual stars, solar systems, and black holes to the grandest possible scale, the four-dimensional continuum of space-time displays its most vast and surprising behavior. In classical physics, the universe was assumed to be an infinite, unchanging and static void within which celestial objects existed. Even Albert Einstein initially shared this bias toward a static universe. When he applied his newly formulated general theory of relativity to the cosmos as a whole in 1917, he discovered to his dismay that his field equations naturally predicted a universe that was inherently dynamic, one that must either expand under its own momentum or contract under the attractive weight of its own gravity. To force his equations to yield a static, eternally stable universe, Einstein inserted a mathematical fudge factor known as the cosmological constant, represented by the Greek letter lambda. This constant represented an innate, repulsive energy inherent to space itself, designed to perfectly counterbalance the inward pull of gravitational attraction across cosmic distances. However, 12 years later, astronomical observations shattered the assumption of a static universe forever. In 1929, American astronomer Edwin Hubble, working at the Mount Wilson Observatory in California, conducted a systematic study of distant galaxies. By measuring the light emitted by these remote stellar systems, Hubble made two groundbreaking discoveries. First, the light from almost every distant galaxy was shifted toward the red end of the electromagnetic spectrum, a phenomenon known as cosmological redshift. Second, the velocity at which a galaxy appeared to be moving away from Earth was directly proportional to its distance from Earth. A galaxy twice as far away was receding twice as fast. A galaxy 10 times as far away was receding 10 times as fast. This linear relationship became known as Hubble's law. The immediate, intuitive interpretation of Hubble's discovery might suggest that Earth sits at the absolute center of a gigantic explosion, with all galaxies flying away from us through space like debris from a bomb. But general relativity offers a far deeper, more extraordinary explanation. Galaxies are not flying through static space away from a central point. Instead, the fabric of space-time itself is continuously expanding. To visualize cosmological expansion, imagine an uninflated rubber balloon with small coins glued to its outer surface. The coins represent galaxies, and the rubber surface represents two-dimensional space. As you blow air into the balloon, the rubber stretches in all directions. The coins themselves do not move across the rubber surface, they remain fixed in place. Yet, as the rubber between them expands, the distance between every single coin grows larger. From the perspective of any individual coin, every other coin appears to be moving away, with more distant coins receding at faster speeds, simply because there is more stretching rubber between them. This distinction between motion through space and the expansion of space is fundamental to cosmic physics. The recession speed of distant galaxies is not governed by the local speed limit set by special relativity. Galaxies far enough away from us are being carried apart by the expansion of space-time at velocities that exceed the speed of light. This does not violate Einstein's universal speed limit because no physical object is traveling through space faster than c. Special relativity dictates that no information or matter can move through space faster than light relative to a local reference frame. But general relativity places no limit on the rate at which the fabric of space-time itself can expand. Cosmological redshift is a direct physical manifestation of this spatial expansion. As a photon of light travels across billions of light-years of intergalactic space to reach our telescopes, it does not lose energy merely through a classical Doppler effect caused by a moving source. Instead, as the photon traverses expanding space, its wavelength is literally stretched along with the expanding fabric of space-time itself. By the time the light reaches Earth after a journey of billions of years, its original optical wavelength has been elongated into longer, redder, lower energy waves. For nearly 7 decades following Hubble's discovery, the central debate in cosmology focused on determining the precise rate of cosmic expansion and calculating how fast the gravitational pull of all the matter in the universe was slowing that expansion down. Physicists assumed that the Big Bang had imparted an initial outward expansion, but the mutual gravitational attraction of billions of galaxies, dark matter and gas must be continuously acting as a cosmic brake. The ultimate fate of the universe hinged on a single question. Was there enough matter in the universe for gravity to eventually halt the expansion and pull everything back together into apocalyptic Big Crunch? Or would the universe expand forever, gradually slowing down as it drifted toward a cold, dark Big Freeze? In 1998, two independent international teams of astronomers, the High Z Supernova Search Team and the Supernova Cosmology Project, set out to answer this question. They utilized distant Type 1a supernovas as standard candles, exploding stars of known uniform intrinsic brightness, to measure how the expansion rate of the universe had changed over cosmic history. The results of their measurements shocked the scientific world to its core. The expansion of the universe was not slowing down under the influence of gravity. It was speeding up. Roughly 5 billion years ago, the universe shifted gears. The cosmic expansion transitioned from a decelerating phase to an accelerating phase. Space-time was expanding faster and faster with each passing second, as if some unknown repulsive physical entity was pushing the cosmos apart across vast intergalactic distances. The leaders of these observational teams were awarded the Nobel Prize in Physics in 2011 for this revolutionary discovery. To account for cosmic acceleration, theoretical physicists resurrected Einstein's discarded cosmological constant, recasting it as the manifestation of a mysterious substance that now dominates the universe: dark energy. Dark energy is currently understood as a pervasive, invisible energy density that fills all of empty space homogeneously. Unlike ordinary matter and dark matter, which dilute and become less dense as the universe expands, dark energy appears to maintain a completely constant energy density per unit volume of space. As the universe expands and creates more empty space, the total amount of dark energy grows proportionally, exerting a uniform negative pressure that drives the acceleration of spacetime. According to the precision data collected by modern space observatories, most notably the Wilkinson Microwave Anisotropy Probe and the Planck satellite, dark energy constitutes approximately 68.3% of the total mass energy content of the universe. Dark matter accounts for roughly 26.8%, while all the baryonic matter we can see, every star, planet, galaxy, gas cloud, and living organism combined, makes up a paltry 4.9% of existence. We live in a universe whose dominant component is an invisible form of energy tied directly to the quantum properties of empty spacetime. The Planck satellite arrived at these precise percentages by mapping the cosmic microwave background, or CMB. The cosmic microwave background is the oldest light in the universe, emitted roughly 380,000 years after the Big Bang, when the expanding universe cooled down to around 3000 Kelvin, allowing protons and electrons to combine into neutral hydrogen atoms and letting photons stream freely through space for the first time. The cosmic microwave background provides a pristine snapshot of the infant universe, preserved as a uniform bath of microwave radiation bathing the sky from every direction at a temperature of approximately 2.725 Kelvin above absolute zero. Crucially, the CMB contains tiny temperature fluctuations, variations of merely a few microkelvins, that correspond to subtle density variations in the early universe. By analyzing the angular power spectrum of these microscopic temperature fluctuations, cosmologists can perform a direct geometric test to determine the overall spatial shape of our observable universe. In general relativity, the geometry of the entire cosmos is determined by its total density of mass and energy relative to a critical density threshold. There are three primary geometric possibilities for the overall shape of spacetime on a cosmological scale. If the total energy density of the universe exceeds the critical density, gravity dominates and spacetime curves inward on itself like a giant four-dimensional sphere. This is a closed universe with positive spatial curvature. In a spherical universe, parallel light rays eventually converge, and the interior angles of a cosmic triangle add up to more than 180 degrees. If the total energy density is less than the critical density, spacetime curves outward like a four-dimensional saddle. This is an open universe with negative spatial curvature. In a hyperbolic universe, parallel light rays diverge and the interior angles of a cosmic triangle add up to less than 180 degrees. If the total energy density precisely equals the critical density, spacetime exhibits no overall global curvature. This is a flat universe with zero spatial curvature. In a flat universe, Euclidean geometry holds true across cosmic distances. Parallel light rays remain parallel forever, and the interior angles of a cosmic triangle add up to exactly 180 degrees. The high-resolution data gathered by the Planck satellite mapped the exact physical size of the acoustic hot and cold spots in the cosmic microwave background. Because the distance the light travelled over 13.8 billion years is known precisely, cosmologists could measure the apparent angular size of these spots on the sky. If the universe were closed and positively curved, the cosmic curvature would act like a giant magnifying lens, making the spots appear larger than their intrinsic size. If the universe were open and negatively curved, the curvature would act like a diverging lens, making the spots appear smaller. The Planck observations revealed that the observed angular size of the fluctuations matches the calculated intrinsic size with breathtaking precision, down to a margin of error of less than 0.4%. The observable universe is spatially flat. This spatial flatness presents a profound cosmic mystery. For the universe to remain flat after 13.8 billion years of expansion, the energy density in the fraction of a second following the Big Bang had to match the critical density to within 1 part in 10 to the 56th power. To explain this astonishing fine-tuning, theoretical physicists proposed the theory of cosmic inflation, which posits that the infant universe underwent a brief, exponential burst of rapid expansion, stretching any initial spatial curvature flat, much like blowing up a giant balloon stretches its surface so flat that a local observer sees no curve. Yet, despite these brilliant observational triumphs, mapping the expanding universe, discovering dark energy, and measuring the spatial flatness of the cosmos through the cosmic microwave background, a devastating conceptual crisis looms over cosmology. Our smooth, continuous geometric description of classical spacetime completely breaks down when we attempt to zoom into the smallest physical scales imaginable, exposing an irreconcilable conflict between Einstein's general relativity and the laws of quantum mechanics. For over a century, modern physics has rested upon two overwhelmingly successful structural pillars. On the macroscopic scale of planets, stars, galaxies, and the universe as a whole, Albert Einstein's general theory of relativity reigns supreme. It portrays spacetime as a smooth, continuous, deterministic four-dimensional geometric fabric that bends and warps dynamically under the presence of mass and energy. On the microscopic scale of atoms, electrons, quarks, and fundamental fields, quantum mechanics reigns supreme. It describes the subatomic world as inherently probabilistic, discrete, non-local, and governed by inescapable uncertainties. Individually, both theories have passed every single experimental test thrown at them with astonishing mathematical accuracy. General relativity accurately predicts the precession of Mercury's orbit and the behavior of black holes, while quantum electrodynamics predicts physical constants to more than 12 decimal places. Yet, despite their individual brilliance, these two descriptions of physical reality are completely, fundamentally incompatible with one another. They operate on mutually exclusive mathematical principles and philosophical assumptions. If you attempt to combine the mathematical equations of general relativity directly with the equations of quantum mechanics, the mathematics completely falls apart, yielding nonsensical infinite values that cannot be eliminated through standard mathematical techniques. This irreconcilable conflict represents the single greatest crisis in fundamental theoretical physics. The core of the problem stems from how each framework conceptualizes the nature of space, time, and physical measurement. In general relativity, spacetime is a smooth, continuous manifold. You can divide a distance or a time interval into infinitely smaller fractions without ever encountering a fundamental structural limit. Furthermore, classical spacetime is strictly deterministic. If you know the precise distribution of mass and energy throughout space at a given instant, Einstein's field equations allow you to calculate the precise geometry of spacetime at any point in the past or future with complete certainty. Physical variables have definite, well-defined values at every single location. Quantum mechanics utterly rejects this smooth, deterministic picture of reality. Central to quantum theory is the Heisenberg uncertainty principle, formulated by Werner Heisenberg in 1927. The uncertainty principle establishes an absolute physical limit on how precisely certain pairs of complementary physical variables, such as a particle's position and momentum, or an event's energy and duration, can be simultaneously known. The more accurately you measure where a particle is, the less accurately you can know how fast it is moving, and vice versa. Crucially, the uncertainty principle is not an artifact of imperfect measuring equipment or human technological limits. It is a fundamental, inescapable law of nature. At the quantum level, physical quantities do not possess definite, fixed values until they are measured. Instead, particles exist as diffuse clouds of probability described by mathematical wave functions. Reality at its smallest scale is inherently fuzzy, fluctuating, and unpredictable. When physicists attempt to apply the rules of quantum mechanics to the smooth geometric continuum of general relativity, this fundamental quantum fuzziness creates chaotic havoc. In classical general relativity, empty space, a complete vacuum, is entirely flat, motionless, and serene. If there is no mass or energy present, there is no space-time curvature. Space is completely still. But in quantum mechanics, absolute nothingness cannot exist. According to the energy-time formulation of the Heisenberg uncertainty principle, the energy contained within a given volume of space cannot remain fixed at precisely zero for any non-zero duration of time. Instead, the quantum vacuum is a boiling, chaotic sea of rapid, spontaneous energy fluctuations. Virtual particles, pairs of matter and antimatter particles, spontaneously pop into existence out of the vacuum, borrow energy from the universe for a fleeting fraction of a second, collide with one another, and annihilate back into nothingness before their existence violates the conservation of energy. These vacuum fluctuations are not theoretical fictions. They produce real, measurable physical effects, such as the Casimir effect, where two uncharged metal plates placed tiny fractions of a millimeter apart in a vacuum are pushed together by the imbalance of virtual particle pressures. At human scales, or even at the scale of an atom, these microscopic vacuum fluctuations are far too tiny to affect the smooth curvature of spacetime described by Einstein. At these larger scales, spacetime acts like a vast, smooth ocean surface that appears completely flat when viewed from a high-altitude aeroplane, despite containing billions of microscopic molecular collisions. However, if you zoom in closer and closer to the physical structure of space, the smooth geometric description begins to break down. As you probe smaller spatial distances, you are simultaneously probing higher energy scales, making quantum vacuum fluctuations increasingly violent and energetic. In 1955, the renowned American theoretical physicist John Archibald Wheeler realized that if you zoom in all the way down to the ultimate microscopic boundary of space, a distance known as the Planck length, the smooth canvas of space-time vanishes entirely. The Planck length, derived by combining Newton's gravitational constant, Planck's constant, and the speed of light, is an unimaginably tiny scale, approximately 1.6 times 10 to the negative 35 meters. To put the Planck length into perspective, if a single subatomic proton were magnified to the size of the entire observable universe, the Planck length on that scale would still be roughly the height of a typical average human being. It is the absolute smallest physical distance scale that can exist within current theoretical models. At the Planck scale, quantum vacuum fluctuations become so violently energetic that their local mass-energy density becomes concentrated enough to curve spacetime drastically on a microscopic level. Wheeler coined the term quantum foam to describe the chaotic, turbulent reality of spacetime at this fundamental boundary. Within the quantum foam, space is no longer a smooth, passive, three-dimensional grid. The geometry of spacetime fluctuates wildly and continuously. Microscopic regions of space warp, twist, and tear apart, spontaneously forming and destroying microscopic wormholes, virtual black holes, and multi-dimensional geometric bubbles that exist for mere Planck units of time. roughly 10 to the negative 43 seconds. In the quantum foam, classical notions of geometry collapse entirely. The very concepts that form the backbone of everyday reality, up and down, left and right, before and after, lose all physical meaning. Spatial points can no longer be clearly separated or localized, and time ceases to flow as a smooth, continuous sequence of moments. Instead, time itself becomes digitized, probabilistic, and hopelessly tangled with the chaotic fluctuations of microscopic space. This microscopic chaos reveals the core paradox that keeps theoretical physicists awake at night. General relativity assumes that spacetime is smooth at all scales, allowing physicists to construct precise differential equations based on continuous functions. But quantum mechanics proves that spacetime cannot be smooth at the Planck scale. If you try to calculate the gravitational force or curvature within the quantum foam using Einstein's field equations, the inputs from quantum uncertainty feed back into the geometric calculations, causing the numbers to explode to mathematical infinity. In classical field theories, infinities can sometimes be removed through a mathematical technique called renormalization, which effectively absorbs the troublesome infinities into measured physical properties like mass or charge. Quantum electrodynamics relies heavily on renormalization to produce its astonishingly accurate predictions. However, when physicists attempt to renormalize general relativity, the technique fails completely. Because gravity is not just a force existing within space, but is the very geometry of space itself. Every single quantum fluctuation alters the background geometry in which the next fluctuation occurs. This creates an endless, cascading loop of infinite terms. General relativity is fundamentally non-renormalizable. This mathematical breakdown is a clear, unyielding warning sign from nature. It tells us that general relativity and quantum mechanics are not complete descriptions of reality. They are effective field theories, brilliant approximations that work exceptionally well within their respective domains, but fail when pushed to extreme limits where immense mass is compressed into microscopic scales. To understand what happens at the center of a black hole, to describe the absolute moment of the Big Bang, or to reveal the true fundamental building blocks of space and time, physics requires a revolutionary breakthrough, a unified theory of quantum gravity capable of bridging the gap between the smooth geometric continuum of Einstein and the chaotic probabilistic world of the quantum foam. Faced with the mathematical deadlock between general relativity and quantum mechanics, theoretical physicists have spent decades constructing new theoretical frameworks designed to reconcile the smooth geometry of gravity with the discrete, probabilistic nature of the quantum realm. Rather than viewing space and time as fundamental features of reality, these frontier hypotheses propose that spacetime itself may be an emergent property, a macroscopic manifestation built from even more fundamental microscopic entities. The two most prominent and heavily researched candidate theories addressing this challenge are string theory and loop quantum gravity. String theory approaches the problem of quantum gravity by fundamentally reimagining the basic building blocks of matter and energy. Standard quantum field theory treats fundamental particles, such as electrons, quarks, and photons, as zero-dimensional point particles with mass, charge, and spin concentrated at infinitely small spatial coordinates. While this point-particle approximation works exceptionally well across low-energy atomic physics, it becomes the primary source of infinite mathematical divergences when gravity is introduced. Because point particles have zero physical radius, two particles can theoretically get infinitely close to one another, causing their gravitational interaction strength to skyrocket to infinity. String theory resolves this issue by replacing zero-dimensional point particles with one-dimensional vibrating strings of energy. These strings are unimaginably minuscule, operating at scales near the Planck length, roughly 10 to the negative 35 meters. Just as a single string on a violin can vibrate at different resonant frequencies to produce different musical notes, an A, a C, or an E, a single fundamental string can vibrate in different modes to manifest as different physical particles. One vibration mode gives the string the mass and charge of an electron. A different vibration mode turns it into a quark. Another vibration mode creates a photon. Crucially, String theory naturally predicts a specific vibrational mode whose physical properties match those of a hypothetical massless particle with a spin of 2, the graviton. The graviton is the theoretical quantum mediator of the gravitational force. In string theory, gravity is not artificially added to the framework. It emerges unavoidably from the mathematics of vibrating strings, making string theory a compelling candidate for a unified theory of everything. Because strings have a finite physical length rather than zero volume, their interactions are smeared out over a small region of space. When two strings interact, they merge and split smoothly like soap bubbles, eliminating the zero-distance infinities that plague point-particle gravitational equations, and allowing gravity to be combined with quantum mechanics without producing mathematical absurdities. However, for the mathematics of string theory to remain internally consistent and free from quantum anomalies, the strings must vibrate in more than the 3 spatial dimensions of everyday experience. Depending on the specific mathematical formulation, string theory requires extra spatial dimensions, specifically 9 spatial dimensions plus 1 temporal dimension in superstring theory, or 10 spatial dimensions in M theory. To explain why we only observe 3 spatial dimensions, up and down, left and right, forward and backward, string theorists propose the concept of compactification. This hypothesis posits that immediately following the Big Bang, 3 spatial dimensions expanded to macroscopic cosmic scales, while the remaining extra spatial dimensions remained tightly curled up, or compactified, at subatomic scales near the Planck length. To visualize compactification, consider a long garden hose stretched out across a lawn, viewed from a distance of several hundred yards. From that distance, the hose appears as a simple one-dimensional line. An object on the hose can only move forward or backward. However, if an ant crawls on the surface of the hose and you inspect it through a magnifying glass, you discover a hidden circular second dimension wrapping around the circumference of the hose. The ant can move not only forward and backward along the length of the hose, but also around its circular width. In string theory, every point in our familiar 3-dimensional space contains these hidden, extra-spatial dimensions curled up into intricate, multi-dimensional geometric shapes known as Calabi-Yau manifolds. The specific geometric shape of these compactified manifolds dictates how strings vibrate, thereby determining the fundamental physical properties of our universe, such as particle masses, charge strengths, and force constants. While string theory offers a breathtakingly unified vision of physics, it possesses a notable conceptual feature. It is typically formulated as a background-dependent theory. It describes strings moving and vibrating within a pre-existing fixed spacetime geometry. In contrast, loop quantum gravity takes a fundamentally different philosophical and mathematical approach. Originating from the works of physicists Abe Ashtekar, Lee Smolin, and Carlo Rovelli, loop quantum gravity is explicitly background independent. It adheres strictly to the core insight of general relativity. Gravity is not a force operating inside space. Gravity is the dynamic geometry of space itself. Therefore, a true quantum theory of gravity should not assume a pre-existing space-time background. Instead, space itself must be built directly from quantum mechanics. Loop quantum gravity achieves this by applying quantum principles directly to the Einsteinian gravitational field. According to this framework, space is not a smooth, infinitely divisible continuous fabric. Just as matter is made of discrete atoms rather than continuous fluid, space itself is quantized. It is made of fundamental, indivisible atoms of space. In loop quantum gravity, the continuous gravitational field lines of general relativity are replaced by discrete loops of quantum gravitational force. When these loops intersect and interlock with one another, they form a dynamic mathematical network called a spin network. A spin network is a mathematical graph consisting of nodes connected by edges, labeled with quantum spin numbers. The nodes of the network do not exist in space. Rather, each individual node is a discrete chunk of spatial volume, measuring roughly 1 Planck volume, or 10 to the negative 105 cubic meters. The edges connecting the nodes represent the boundary surfaces between these spatial chunks, defining discrete quantum units of area. Because spatial volume and surface area are quantized into discrete units in loop quantum gravity, space cannot be divided down indefinitely. there is an absolute minimum possible volume of space and an absolute minimum possible surface area below which space simply cannot exist. When time is incorporated into this picture, the static spin network evolves through discrete quantum steps, transitioning from one network configuration to another. This evolving four-dimensional quantum web is known as a spin foam. In the spin foam model, time does not flow smoothly as a continuous tick of a clock. Instead, time advances in discrete indivisible leaps, Planck time intervals of roughly 10 to the negative 43 seconds, much like the individual frames of a motion picture film. Loop quantum gravity alters our understanding of extreme cosmic phenomena. Because space is quantized into indivisible units that resist being compressed into zero volume, the physical gravitational singularities predicted by classical general relativity at the centers of black holes and at the Big Bang are eliminated entirely. When a collapsing star compresses matter down to the Planck scale, the discrete quantum chunks of space exert a powerful repulsive quantum force, a phenomenon known as polymer pressure. Instead of collapsing into a point of infinite density, the star reaches a maximum density limit and rebounds outward in a cosmic event known as a Big Bounce, transforming the Big Bang from a moment of creation into a transition from a preceding collapsing universe. Both string theory and loop quantum gravity offer brilliant, mathematically rigorous visions of quantum spacetime. String theory unifies all forces by introducing extra spatial dimensions and vibrating strings, while loop quantum gravity quantizes the fabric of space itself without needing extra dimensions or background geometry. Yet both theories face the exact same fundamental criticism from experimental scientists. Because they operate at the elusive, microscopic scale of the Planck length, gathering direct empirical proof remains extremely difficult, keeping these frontier models within the realm of unproven theoretical hypotheses. Beyond string theory and loop quantum gravity, theoretical physicists are exploring even more radical concepts that challenge our most basic assumptions about the fundamental architecture of reality. Chief among these frontier ideas are the holographic principle and the hypothesis that quantum entanglement actively weaves the physical fabric of space-time itself. These theories propose that three-dimensional space, along with the force of gravity, might be an elaborate physical illusion, an emergent phenomenon generated by simpler quantum processes occurring on distant boundaries. The holographic principle originated in the 1990s through the groundbreaking theoretical work of Nobel laureate Gerard 't Hooft and Stanford University physicist Leonard Susskind. The concept emerged directly from a deep thermodynamic paradox surrounding black holes, first uncovered by Stephen Hawking and Jacob Bekenstein in the 1970s. In classical physics, the amount of information or entropy that a physical system can store scales directly with its three-dimensional volume. If you double the size of a room, you double the volume of space inside, allowing you to store 8 times as many books or particles. However, when Bekenstein and Hawking calculated the maximum theoretical entropy, the total information capacity, of a black hole, they discovered something completely unexpected. The maximum information a black hole can store is not proportional to its three-dimensional volume. Instead, it is strictly proportional to the two-dimensional surface area of its event horizon. This mathematical result led 't Hooft and Susskind to make a profound physical deduction. If a black hole, which represents the densest possible storage of matter and energy in a given region of space, has an information capacity determined entirely by its two-dimensional boundary surface, then perhaps the entire universe operates under the same rule. The holographic principle posits that all the physical events, matter and gravity occurring within a three-dimensional volume of spacetime can be fully described and encoded on a lower-dimensional two-dimensional boundary surrounding that region. Just as a standard optical hologram projects a full three-dimensional image from a flat two-dimensional piece of plastic when light shines through it, our experience of a three-dimensional universe, filled with physical objects moving through space, may simply be a macroscopic, emergent projection generated by quantum information residing on a distant two-dimensional boundary surface. In 1997, Argentine theoretical physicist Juan Maldacena brought the holographic principle into sharp mathematical focus by discovering the anti-de Sitter conformal field theory correspondence, commonly known as the ADS-CFT correspondence or gauge-gravity duality. Maldacena demonstrated a precise mathematical equivalence between two completely different physical theories. On one side of the duality was a five-dimensional universe containing curved spacetime, vibrating strings, and gravitational forces, a theory governed by general relativity in anti-de Sitter space. On the other side of the duality was a four-dimensional quantum field theory operating strictly on the boundary of that universe, a theory containing no gravity whatsoever, governed purely by quantum particle interactions. Maldacena proved that every complex gravitational event occurring inside the five-dimensional volume had an exact one-to-one mathematical translation into a particle interaction occurring on the four-dimensional gravity-free boundary. A black hole collapsing in the interior corresponded precisely to a thermal plasma on the boundary. The mathematical duality proved that gravity and higher-dimensional spacetime are not fundamental building blocks of nature. They are emergent features, computational projections generated by lower-dimensional quantum fields. This realization led physicists to ask a profound follow-up question. If space-time is an emergent projection generated by quantum information, what specific quantum phenomenon acts as the physical glue that holds the continuum of space-time together? The answer appears to lie in one of the most mysterious features of quantum mechanics: quantum entanglement. Quantum entanglement occurs when two or more particles become intertwined such that their physical states are intrinsically linked, regardless of the physical distance separating them. If two entangled photons are created and sent to opposite sides of the universe, measuring the spin state of one photon instantly dictates the spin state of the other, defying classical intuitions about spatial separation. Albert Einstein famously rejected this non-local behavior, calling it spooky action at a distance. In recent years, physicists such as Mark van Ramsdonk, Shinsei Ryu, and Tadashi Takayanagi have demonstrated that quantum entanglement may be the fundamental force that creates physical space itself. In 2010, Van Ramsdonk conducted a theoretical experiment using the ADS-CFT correspondence framework. He examined what happens to the bulk five-dimensional spacetime when you slowly reduce and eliminate the quantum entanglement between the particles on the four-dimensional boundary. The mathematical results were astonishing. As the quantum entanglement between the boundary particles was reduced towards zero, the corresponding three-dimensional spacetime in the interior began to pinch off, fracture, and tear apart. If you completely remove quantum entanglement from the boundary theory, the smooth geometric continuum of spacetime dissolves entirely into disconnected, isolated points. Spacetime exists only because quantum entanglement holds neighboring regions of space together. This connection culminated in the famous ER-EPR conjecture, proposed in 2013 by Juan Maldacena and Leonard Susskind. The acronym ER refers to Einstein-Rosen bridges, the theoretical mathematical solutions derived by Albert Einstein and Nathan Rosen in 1935 describing wormholes, or shortcuts connecting two distant regions of spacetime. The acronym EPR refers to Einstein-Podolsky-Rosen quantum entanglement, described in the same year. The ER-EPR conjecture proposes that these two seemingly disparate concepts are actually identical physical phenomena viewed through different theoretical lenses. Every time two subatomic particles become entangled, they are connected by a microscopic quantum wormhole. If you entangle thousands of particles together and weave their quantum states into a complex interconnected web, these microscopic wormholes coalesce and smooth out, generating macroscopic, continuous regions of three-dimensional space. In this view, space is not a pre-existing container or an independent physical object. Space is literally woven out of threads of quantum entanglement. The smooth, flexible fabric of space-time described by Einstein's general relativity is simply the macroscopic manifestation of vast networks of subatomic quantum information linked across the cosmos. These frontier hypotheses, the holographic principle, gauge-gravity duality, and the entanglement creation of spacetime, represent a complete paradigm shift in fundamental physics. They suggest that space and time are not the ultimate foundations of existence, but rather emergent properties arising from an underlying non-spatial quantum reality, pointing toward a future where our complete understanding of the universe must be built from the ground up. Albert Einstein transformed space and time from static, unyielding stages into a unified, dynamic continuum capable of bending, stretching, and rippling across the cosmos. General relativity allowed us to understand the cosmic choreography of planets, calculate the extreme distortion surrounding black holes, map the accelerating expansion of the universe, and build satellite technology that navigates our daily lives. Yet, despite more than a century of brilliant experimental confirmations, the ultimate nature of spacetime remains one of the greatest unsolved mysteries in human history. When we attempt to view spacetime at the microscopic Planck scale, the smooth geometry of Einstein breaks down into the chaotic, boiling uncertainty of the quantum world. Frontier physics suggests that spacetime may not be fundamental at all, but rather an emergent projection woven out of quantum entanglement and information residing on distant boundaries. We have learned to calculate the curvature of spacetime with extraordinary precision, but we are only beginning to uncover what this four-dimensional fabric is truly made of. Science marches forward by confronting these deep unknowns, constantly testing the limits of our knowledge. If you enjoyed exploring the fabric of the universe with us, consider liking this video and subscribing to the channel for more scientific deep dives. Before you go, leave a comment below letting us know your precise coordinates in space and time, where and when in the universe you are watching this right now.